Hi, my name is Calvin Carpenter, and for this video, we're going to be applying the Crank-Nicolson method for differencing. And we're going to be trying to prove that we're unconditionally stable for any value of r. And in the previous video for finite differencing, we found that when r was greater than 0.5, then our equation became very unstable. And so we're going to try and fix that in the video using the crank. This video, we're going to be using the same breakdown of this equation that you see on your screen here. So I'm just going to go ahead and write that out. If you missed it, we broke down this equation in the finite differencing. So it's going to be t of L at one timestamp in the future minus t of L at the current timestamp over change in time, our alpha, over 2, big parenthesis, of our give L t of the one block to the right at one timestamp in the future minus 2 of our current block at our current timestamp plus temperature of block to the left. Sorry, these are future timestamps over our change of position squared. That's minus temperature of the block to the right at the current timestamp minus 2 times the temperature of the current block at the current timestamp plus temperature block to the left current timestamp over change in position squared. And for this, I'm going to set r equal to alpha over 2 times delta t over delta x squared. So now I'm going to rewrite this equation subbing r into it. So we have our temperature at our current block of interest, one timestamp of the future, equals the temperature of our current block at our current time plus r times the temperature of the block to the right, one timestamp in the future minus 2 times our current block, one timestamp in the future, plus the temperature of the block to the left at one timestamp in the future, and then we're going to subtract our terms at our current timestamp. So temperature of our one block to the right at our current timestamp plus 2 for current block at our current timestamp minus the temperature of the block to the left at our current timestamp. All right, so that is our equation rewritten with r substituted in for alpha over 2 times delta t over delta x squared. So now what we can do is move these terms over to the left-hand side to kind of simplify it down a little bit. So that will leave us with negative r times our block to the right, 1 timestamp in the future, plus parentheses 1 plus 2r times our temperature at our current block, 1 timestamp in the future, minus r times our temperature of our block to the left at our current timestamp. This equals, sorry, I think that's, yeah, it's supposed to be plus 1. Then that equals r times the temperature of block to the right at our current timestamp plus 1 minus 2r times the temperature at our current block at our current timestamp plus r times the temperature of a block to the left at our current timestamp. So this is our, I know this is kind of big, but we're going to break this equation down into something called a called a tridiagonal matrix, and that will allow us to analyze this equation further. I'm going to break this up into matrices. Scroll down a little bit so you can see. Got to kind of draw these a little big. I don't want to run out. All right, so we're going to break this equation up into 3 different arrays. And I will show you what it will consist of in a moment. Okay. So, let me just scroll over a bit so you can see this. So we're going to start at L equals 1, L equals 2, end up L equals W. Because if you remember in my finite differencing video, W was the end length of our bar to 0. And so if you remember, the temperature on the right over here was 400 Kelvin, and then temperature on the left was 350 Kelvin. And then all of the middle ones were 300 Kelvin. So going back up to the matrix here, I'm just going to start with this middle one here. So our first value is going to be our temperature at position 1, then we'll go to our temperature position 2, and we'll go all the way down to the temperature position W. And so now we're gonna fill in the matrix on the right, just because it's a little bit easier than the one on the left. So for this one, you just in our big equation there, you just put in those L values for T. So we get for L equals 1, we get R T2 plus 1 minus 2R times T1 plus R T0. Then for L equals 2, we get R times T3 plus 1 minus 2R times T2 plus R times T1. And that goes all the way down until L equals W. Okay, now this first matrix is where things get a little spicy. So basically, there's going to be some terms of L where the temperature beforehand and after will exist, and then there's some terms where it won't. So that'll come into play here. So for the first term of our matrix here, we sub in L for the current block, because at L equals 1, there is no previous block. So we get the coefficient for that is 1 plus 2R. And then for a block to the right, our value is negative R. And then the rest of the terms are going to be 0. I don't have enough room to write infinite amount of zeros, so I'm just going to write dot, dot, dot. For L equals 2, we do have a block to the left of L equals 2. So we're going to have a negative R, a 1 plus 2R, and then another negative R, and then we'll have our zeros. And we're just going to do L equals 3 as well. So for L equals 3, we're going to start off with a 0 because it's going to be moved over. Then we'll have negative R, 1 plus 2R, and then negative R, 0. I might as well just here do this. There we go, so you can line up all the values there. So basically this array is analyzing every block that we split up in the bar. And so what we're going to do with this, since I can't physically solve this, we're going to move over to Collaboratory, and we're going to use some pretty cool plugins to help us solve this matrix. We've moved over to Collaboratory. We're going to import Utley. Thoughts. And as well. All right, now we're gonna set our variables. Functions in our pod. We're gonna set stamp 1000. And then we're gonna set our R value equal to 1. And I know that's higher than last time. I know that we had a limit of 0.5, but we'll be able to do this. Then we'll value set our 50 on the left. Profile initially on the right. Right. Now, we're going to start setting up our array. So let's just define so O start with 3. Now we'll set of R, if you remember from our equation. This was the next value of our equation. Now, our equation was also negative. Okay, now we can do this is our right side of the equation. R times 2 onward. Plus this is just our equation for how our Q value is going to update as our loop goes on, which we're going to use a for loop, actually. So 0 plus R times T of 0. Now we define our Q of negative is equal to showing how we're going to add to it. So like whenever the for loop happens. Negative 1. Okay. Should work. See what's wrong here. There we go, that worked. Okay. Sorry, just had to add double parentheses to that one. Now make our figure. Subplot. Same as last time, we'll do and then add our subplot. We're gonna data point with lines again. And then our initial. You can see our figure, our plot function does work. So now I'm just going to add in our for loop. Okay. Range. T from solve. Okay. So we're going from the first iteration and we're solving our next iterations are going to be all the values for P and for Q. And so for every iteration in this for loop, we're going to want to update our value for Q, which we can just copy and paste down in here. And same thing as yeah. So we're going to set our x-axis, our y-axis, code. The values are connected by lines. And finally, the name. That iteration. Okay. Works, cool. Show our if this works. Okay, perfect. So as you can see, this is going to be the heat diffusion through our rod, and we're going to see if we can actually get this to approach a more steady state. So like more of the lines are becoming linear up with this top red one. So we're going to increase timestamps, and then in turn, where's it at? To increase this value. Okay, so there we got a linear one. Wait, did I not update this one? No, I didn't. There we go. Okay, so as you can see, a lot of these reached steady state. So we're actually going to increase our R value as well, just to see what happens. Going to go like 3. Okay, so actually, if you see right here, I guess if the R value gets too high, then the first jump that the simulation makes gets overshot. So you need to be careful with those first initial R values. Make sure they don't get too high. But for the most part, this graph has reached steady state. So sweet. I guess we're done with the Crank-Nicolson method for the finite differencing equation. Thanks for watching.